morning. So, I am Dr. Anirban Mitra from Physics Department of IIT Roorkee. So, today I will talk about the laser produced plasma and pulse laser deposited thin films. This plasma is also almost become synonymous with the lasers. After the discovery of lasers, this plasma, this field also become very much interesting, because it is very easy to generate plasma with the help of laser. Laser, we know that it is a light amplification by stimulated emitted radiations, which is nothing but a light, and it is a type of coherent light where the phase relations between all the photons are maintained, and it can produce a huge amount of energy within a very small region. So, that is why it is very much useful for generation of plasma. Of course, there are several other techniques for generation of plasma apart from the laser, that is with the help of electrical discharge inside a gas. So, you can produce the gas. Also by sputtering, we can have a RF sputtering type of equipment where you can accelerate the ions and which can bombard a solid target and which can also generate plasma. But in those cases, there is some limitations. Sometimes you need a conducting target. So, in case of lasers produced plasma, it is very easy to vaporize any kind of materials, whether it is gas, solids or liquids. So, with a very huge amount of energy within a very small time, you can generate the plasma. Now, with the invention of these short pulse lasers like nanosecond lasers, which can be generated with the help of Q switch or mode locking. So, in the order of 2 to 10 nanoseconds or more than that, you can also generate the picosecond, sub picosecond, that is the femtosecond lasers, which can also very useful for generation of plasma or laser ablating the materials and other things. Here today I will talk more about the pulse laser deposited thin film, which is a very versatile useful technique by using the laser, and where also the knowledge about the laser produced plasmas are also very useful. Now, I will talk about something about the historical background about the pulse laser deposition techniques. This pulse laser deposition techniques, as I have told you, is invented after the development of the pulse laser, very fast pulse laser like Q switch lasers or of the order of 2 to 10 nanoseconds, and which can generate a huge amount of energy. Suppose that lasers which we have in our lab, if it is a 1 joule per pulse in that fundamental wavelength, that is the 1064 nanometer. It is a kind of Nd:YAG lasers where this neodymium are doped in yttrium aluminum garnet, which is a solid state lasers. So, in that lasers we have the pulse repetition rate of 10 hertz and is the pulse width is 10 nanoseconds. So, if 1 joule energy is delivered within 10 nanoseconds, so you can see that it is 0.1 gigawatt, which is a huge amount of power can be generated within a very small time, and this energy can be very useful for generation of plasmas like in solids, liquids or gases. Now, this laser light, if you can focus it like the common lights, you can focus it with the lens. So, it can deliver a huge amount of energy within a very small area. So, that can be almost say 2 to 3 millimeters. So, with this kind of energy, the first successfully the thin film which has been grown is the YBCO, that is the yttrium barium copper oxide, and it is a superconducting thin film. And this pulse laser deposition technique becomes very much interesting and very much useful, and it becomes draws attraction among the scientists after the successful deposition of YBCO, which is very difficult to deposit with other technique, because you can see that it is a yttrium barium copper oxide, which is a room temperature or high temperature, you can say, not room temperature, high temperature superconductor, which was invented in the year of 1987, and these films are very difficult to deposit because it has a 4 type of element like yttrium, barium, copper and the oxygen also. So, all this material should be the stoichiometry of these elements or of these all these materials should be maintained properly. So, what is the advantage of pulse laser deposition technique is that you can deposit the same material as the material of the target. So, you can maintain the stoichiometry or the composition of the material. So, that is the very useful advantage of pulse laser deposition technique. Moreover, it is much more easier to handle compared to the other deposition techniques like RF sputtering and other techniques also, MB, that is the molecular beam epitaxis, chemical vapor depositions and other techniques. So, here you can deposit any kind of material, whether it is a metal, semiconductor, conductor or any kind of material. So, after the successful growth of yttrium, barium, copper oxide, the pulse laser deposition technique become very much useful and it becomes routinely used by the researcher. So, now I will show a video of that pulse laser deposition techniques while we are doing the pulse laser deposition in our lab with the help of a ND third harmonics, that is the 355 nanometer of a ND arc laser, that is the neodymium doped yttrium aluminum garnet. Actually, the actual wavelength, that is the fundamental wavelength, is 1064 nanometer, but you can use the nonlinear crystals to generate the third harmonic of this. So, which is the 355 nanometer. So, which is useful for deposition of thin films, and I will explain that why this wavelength is useful. And you can see that a blue light, that is the blue color plasma is generated. So, you can see the video. So, laser light is coming from this side and then it is falling on the target and then the plasma is generated and then it will, this plasma is ejected from the target materials with a very high velocity and then it will, this is the substrate where we will generally deposit the thin films. So, materials will be ejected at a very high velocity from the target materials. So, and then it will just deposit on the substrate, and this is the your chamber, and we can use the different kind of gas also inside the, sometimes you can use the inert gas like argon or helium to slow down the species which are ejected from the target, or you can use some reactive gases like you can use oxygen or you can use nitrogen also generally. So, to deposit nitride or oxide kind of films, thin films. Here we are depositing zinc oxide and nickel oxide, mainly the oxide based thin films. So, you can see the generation of plasma inside the lab with the help of laser. Now, I will show another video where you can see the generation of the ionization of gas or the plasma of air inside the, simply in the air, just by focusing the laser light. So, you can see the how the huge amount of energy can be focused with the help of a lens within a very small region, and you can generate the plasma of different materials like it can be gas, solids or even liquids. So, here you can say, see this is the lens where with the help of lens the laser beam is focused here, laser beam is focused here and with the help of this lens, and here you can see that a spot is which is glowing here. So, that is the plasma of, it is the plasma of the air. So, this is the another video, you can see that with the help of laser light you can the generation of plasma of air or even of the solids. So, now with this introduction, so slowly I will go more into the details of the deposition procedure of the plasma. of the laser produced plasmas and the pulse laser deposited thin films. So, now what is the mechanism of pulse laser deposition? So, first of all, that your laser beam should be focused onto the target, as I have already mentioned. So, a huge amount of energy should be convert, or it will be focused onto a small area. Now, this after the laser light interact, or it will be absorbed by the materials or the solid targets. So, then it will heat up. So, it will use basically initially it will be just the hitting the target, and then when it will reach the vaporization temperature, initially it will be melt and then it will vaporized, and then the material will injected, and when the material will injected, and then it will further is energy will increase, because this pulse width is very short, it is of the 10 nanosecond. So, initial part of the pulse mainly the energy will be used for the hitting the target, and next part of the pulse will used to generate the plasma and ejecting the materials from with a high velocity. So, you can say that now there will be a plume which will be ablated from the material, and generally it will ablated from the just normal to the target, because in that region your velocity of the materials will be very high, and at the angles the velocities will be small. So, you can see that plasma plume was very highly direct, it is like a conical shape. What you can see in the video, that the plasma shape is like a conical type. So, it will have a angle dependent. So, in when it will the velocity will also depend upon the angles, and the amount of material which will also deposited at the angles are also vary. So, that is also a disadvantage of pulse laser deposition technique, because you can deposit the very good uniform thin film within small areas of 2 to 3 4 millimeter, but further if you want to deposit the very large area thin film, then it may not be so useful, but there are other techniques of the pulse laser deposition like rastering or some by other method. Nowadays, even for industrial purpose, one can generate the large area thin film, and due to that now that laser plasma interactions all also become very much important or very much useful. So, the knowledge of laser plasma interactions, because when initially the plasma will form, and then when the further in that later part of the pulse, when the laser will comes, and then it can absorb by the plasma, which will also further heat the temperature, increase the temperature of the plasma, and it will also can accelerate the ions of the plasma, and then it will deposit on the substrate with a very high velocity. So, initially you can say that all these materials, if it is a compound materials, if it is not an element, single element, like if it is a zinc oxide, copper oxide, aluminum oxide, magnesium oxide, or some yttrium, barium, copper oxides, aluminum nitride, or any other kind of material, or say molybdenum oxides. So, in this it will decompose, or it will decompose into the ions and the electrons, like it can form the for zinc it can form the zinc ions and the oxygen ions and electrons. So, all these ions and electrons, they will move with the different velocity and towards the substrate, and then again it will recombines. So, again it will chemi absorbed or physi absorbed on the substrate, and then they will form again that same material onto the substrate. But there are several parameters which one should maintain for the deposition of thin films. It is not that stoichiometry automatically it will maintain. So, sometimes there are the like in case of oxide thin films, there will be vacancies of oxygen. So, in that case controlling the oxygen pressure is also very important, and then heating the substrate, because when these atoms and all this will recombine on the substrate. So, then it will diffusion process will takes place, and to further promote the diffusion process, sometimes one has to heat the substrate, which will grow, which will helpful in growing very good quality thin films. So, all these things also maintained, and there are certain other parameters like the target to substrate distance, that is also important parameter, because that all these ejected species, they should have sufficient velocity to reach the substrate. So, that also one has to maintain, and then the pressure of the oxygen gas, because sometimes the inert gases like helium, argons, those are using to slowing down these species, plasma species which are ejecting from the target. But if you use, and then so how much will be the pressure? So, depending on, if the pressure is very high, then the all the ejected species may not have the sufficient amount of energy to reach the substrate. Now, if the pressure is very low, so in that case it can also ejected with a very high velocity, and then that may damage the substrate also, and that may not be very useful for the good quality thin film. So, sometimes you have to optimize the background gas pressure, whether it is inert gas, or in case of the reactive gases like oxygens or nitrogens. So, then also you have to maintain the oxygen pressure to control the reactions inside the gases to get a good quality thin films, and also maintaining the exact stoichiometry of the target. So, depending upon the applications and what is the requirement, so one can maintain all these things. And then another parameter, so there are several parameters like the oxygen gas pressure, the target to substrate distance, substrate temperature, and then some laser parameter like choosing the laser wavelength. So, how one can choose the laser wavelength is also important, because that amount of energy which will be initially absorbed by the target, that absorption coefficient should be very high for that particular wavelength. So, generally use that laser wavelength of in the UV region, because generally if we want to deposit the semiconductor or insulators, so their band gaps are quite large. So, one can use the UV lasers. So, generally either XIML laser which have the wavelength of 248 nanometers or 193 nanometers or 308 nanometer, depending upon the different gases, or we use the neodymium doped yttrium aluminum gynion laser, that is the NDR laser. So, which can also generate the 355 nanometer or 266 nanometer in the UV region. So, we can see that there are the effect of background gases, and also the energy is also, laser energy is also very useful. So, you should have, first of all it should be above the threshold, so that it can able to eject the ablate the above the ablation threshold, so that it can be remove or ablate the material from the target, and then it will be have enough energy to form the plasma, and then it will have enough energy to reach to the substrate. So, sometime if one use very high energy, so it can re-ablate the material from the substrate, so it can again damage the film. So, one has to be very careful for choosing all these things parameter, and generally the pulse widths are of the order of nanosecond, but nowadays femtosecond lasers are also available. So, one can use the femtosecond, but the mechanisms for femtosecond lasers are completely different, very much different from the nanosecond lasers. So, mainly here we will talk about the nanosecond laser produced plasmas, and then so already we have discussed that first of all you will have, so all that 3 steps you will have formed in the pulse laser deposition technique. So, it can classified into the 3 stages for the pulse laser deposition of thin film. First of all is the ablation of the material. So, that I have already mentioned that it will target will absorb the laser light, and then it will hit the target with the help of laser, and slowly the temperature will reach to the melting temperature, and then after melting vaporization will takes place, and it will ejected from the target, and then the plasma will form, and then this plasma will expand, and there is another phenomena where it is called it will form a shock waves type. Shock waves will form from the plasma, which will go with a very high velocity and from the target toward the substrate, and then further nucleation and growth which will be occurred onto the substrate. We will describe the small description about the overview of the experimental setup of that pulse laser deposited technique. So, here you can see that there is a ND arc laser. Actually, I have shown you because these lasers we are using in our laboratory in that physics department of IIT Roorkee. So, here we generally use the third harmonic of the ND arc laser. So, it is 355 nanometer, but the 266 nanometers wavelength is also useful, and in 355 nanometer the energy which will use generally of the order of 200 to 300 millijoule per pulse. And so, this system is quite versatile and relatively it is simple compared to other deposition technique. So, you can see that the lasers is just coming and then it will focus with the help of a lens towards the target, and this target holder it will rotate continuously. So, that always the fresh surface of the target should come, otherwise what will happen, there will be a crater will form. So, which will hamper the or which will obstruct the formation of the plasma. So, fresh surface or the polished surface is always required. So, that is why sometimes we have to change the target routinely, or we have to raster or rotate the target continuously, and then you can have rotating substrate holder or the fixed substrate holder also. Rotating means if we want to deposit a very uniform film, so in that case maybe one can rotate the substrate, but it is difficult sometimes because there is a heater is attached with the substrate holder. So, sometimes it is difficult, and there are the observation windows also available through which you can do the diagnostics of plasma. One can do just by doing the spectroscopic measurement, that is the whatever the species are coming from this target. So, one can analyze those species and what is the velocity of this species, what is the temperature of the plasma. So, all these things one can monitor. Sometimes one can monitor in situ while depositing the thin films. So, most of the time we monitor this in situ, these plasmas, and with the help of these things one can find out these parameters like electron temperature and velocity of the ions and densities of these ions and electrons, and these informations are very useful for deposition of the good quality thin film. So, we can use this knowledge further for deposition of better quality of thin film. Now, as I have told you, so there are the wavelengths which are available from the excimer lasers. By changing the gases, excimer lasers are also routinely used. So, because it is very useful, because the wavelengths are available in the ultraviolet range or UV range. So, you can have by changing the gases also you can have different wavelengths, like if you use xenon chloride you can have 308 nanometer, or if you use KrF krypton fluoride you will have 248 nanometer and 193 for argon fluoride if you use, and similarly you have fundamental wavelength for ND arc laser is 1064 nanometer. So, generally we do not use this, but 532 and also visible range it is also 532 nanometer, this is also not very much useful, but more useful is 355 nanometer and 266 nanometers. And the deposition chamber is generally made up with a stainless steel, and it is connected with a vacuum part like a diffusion or the turbomolecular pump. So, up to the 10⁻6 to -8-9 torr you can reach, and then the target holder it should be rotated, and this substrate heater should also be there. Now, initial mechanisms of laser matter interactions. So, when laser will interact with the material. So, generally I will discuss more about the insulators and the semiconductors. So, there can be different kind of transitions, either it can be interband transitions. So, it can go directly from the valence band that electrons which will absorb. So, in the valence band that electrons which will absorb by the materials. So, this laser wavelength which is say 248 nanometers. So, then it will be equivalent to say around 4 point some electron volt, which is much larger than the band gap of the semiconductor and insulator available. Generally like zinc wide band gap semiconductor like zinc oxide, gallium nitride, they have the band gap energy 3.4 electron volt, and that laser energy in the electron volt should be larger than this band gap energy of that semiconductor, so that the electrons which will have sufficient energy to jump from the valence band to the conduction band. And then when it will jump to the conduction valence band to conduction band, then there can be a non-additive radiations by which through the phonon. So, there will be a phonon generations. So, by which it will comes down to another level inside the conduction band, and from there it will again de-excite to the valence band, and so that wavelength which will emit and which will absorb. So, which that emission wavelength will be higher than the absorbed wavelength. Now, there can be also, this is the interband transitions. So, generally if we use the laser wavelength which have the energy greater than the band gap, so then one can expect the interband transition. Now, if we use the so each is generally very much efficient. So, you will have a single photon excitation. Now, if we use the wavelength say 1064 nanometer, so it is around 1 point some electron volt, which is much lower than the band gap. So, then what we require that there will be 2 photon or 3 photon or multi photon excitation. So, in that case you need 2 photon to excite an electron from the valence band to conduction band. So, in that case the laser ablation process or laser vaporization process are not very useful. So, that is why most of the cases one can see that we use the lasers which in the UV region like either 248 nanometer, 193, 355 or 266. So, all these are in the either UV or blue region. So, these are the mainly used. There can be other thing also, sometimes even with the IR laser like 1.06 nanometer can also be useful for deposition of pulse laser deposited thin films when you have some defect state. So, in between the valence band and conduction band, if you have some defect state, so then the laser can be absorbed and by the electrons, and it can go to this defect state and then it will de-excite to the valence band. So, in this process also there if we use the lower higher wavelength or with the lower photon energy, so this process can also be useful. There can be also interband transitions within the conduction band also. So, these are the different mechanism which can takes place. Generally for metals are very highly reflective in either and both either IR or visible regions also, and even in that UV regions also it can the conduction band electrons can block the laser. So, that generally the pulse laser deposition process for metals are slower than the semiconductor or the insulators. So, with this I will just complete. So, thank you very much.